Good morning. My name is K. Purushotham, working as a assistant professor in the Department of Electronics and Communication Engineering from MLR Institute of Technology. What are the different types of demodulators? And before that, what I am going to cover today lecture is, first I am concentrating on coherent detector. The coherent detector which is used for the demodulation of the DSBSC wave. Next, introduction to the SSB modulation. What is the need of SSB modulation? And what is the mathematical expression for the SSB modulation, and what is the bandwidth for the SSB modulation, and what is the power consumption for the SSB modulation, then what is the power saving by using the SSBSC modulation system. So, first the demodulation. Demodulation is the process of extracting the original information from the received signal. By using the different modulators, we are transmitting the AM and DSBSC signals. At the receiver, we are receiving the DSBSC transmitted signal. From the received signal, it is containing the carrier signal and original information signal, which is located in the both sidebands. So here, the original information which is located in the both sidebands can be extracted by using the demodulation technique. So first demodulator what we are using for the extracting the original information from the received signal is coherent detector. What is the meaning of coherent? Coherent is nothing but the carrier whatever we are using, the carrier frequency and phase whatever we are using for the transmitter, same carrier we are using at the receiver side, and that carrier we are multiplying with the received signal. So the carrier whatever we are using at the transmitter side and the carrier whatever we are using at the receiver side should be in phase and should be the same frequency. Okay, that's why the name itself has given coherent or synchronous detector. So here the same carrier signal which is used for the generating the DSBSC signal is used to detect the message signal. Hence, the process of detection is called as a coherent or synchronous detection. So, what is the block diagram for the coherent detection is, here DSBSC wave, that is modulated wave, what we are generated by using the DSBSC modulator and that transmitted, and at the receiver that modulated wave we are receiving, that wave we are applying as the input to the product modulator. Another input signal what we are applying, carrier signal we are applying. The carrier signal AC cos 2 pi FCT plus phi. So phi is the delay or phase. So the signal whatever we are using at the transmitter side, that carrier signal, same carrier signal I am developing here, and that signal I am applying to the input of the product modulator. So what we are getting across the output of the product modulator, DSBSC wave multiplied with the AC cos 2 pi FCT plus phi, that is the V of t. So that V of t is applied to the low pass filter. So we are designing the low pass filter such a way that it is allowing only the message signal through it, and other high frequency signals and power noise, all those things can be eliminated by using the low pass filter. So finally what we are obtaining at the output of the demodulator, the original information what we are transmitted from the transmitter section, that signal only we are obtaining at the receiver output. So here, so let us take the mathematical expression for that. So let DSBSC wave S of t is nothing but AC cos 2 pi FCT into M of t, the signal which is generated by using the DSBSC modulators. Okay, that signal only we are applying as the input to the detector. So what is that signal S of t? S of t is AC cos 2 pi FCT M of t. So what is the M of t? M of t is nothing but AM cos 2 pi FMT. M of t again, how we are representing that? M of t is nothing but AM cos 2 pi FMT. 2 pi FMT. Okay, original information which is located. So the output of the local oscillator is C of t, AC cos 2 pi FCT plus phi. Okay, where phi is the phase difference between the local oscillator signal and the carrier signal, which is used for the DSBSC modulation. And now, so V of t is nothing but the output of the product modulator, what we are getting, V of t. So the V of t is nothing but S of t multiplied with the C of t. S of t multiplied with the C of t. So V of t, how we are representing here? S of t. S of t, what is the S of t? S of t is AC cos 2 pi FCT into m of t multiplied with AC cos 2 pi fct plus phi, the local oscillator which is generating the carrier signal. So now if you are multiplying AC square cos 2 pi fct plus phi into m of t, we are getting. Okay. So now this formula is nothing but cos A cos B. Okay. This formula is nothing but cos A cos B. Cos A plus B plus cos A plus B, we are representing this one. So finally what is the value we are getting here? AC square by 2 cos 4 phi fct plus phi plus cos phi multiplied with m of t. So now AC square by 2 cos phi m of t plus AC square by 2 cos 4 phi fct plus phi into m of t. Okay. These are the two terms we are getting here. So among those two terms, this is the wanted signal which is containing the carrier signal cos phi multiplied with the m of t is the wanted signal. Original information is concentrated in m of t. So this term is unwanted term. This term is unwanted term. This can be eliminated by using low pass filter. This can be eliminated by using the low pass filter. Low pass filter we are designing such a way that it will allow only the modulating signal frequency. So here it is containing the modulated signal and the carrier frequency which is multiplied with the 4, that is nothing but very high frequency. That high frequency can be eliminated by using the low pass filter. Okay. In the above equation, the first term is the scaled version of the message signal. AC square by 2 is nothing but scaling factor. AC square by 2 is nothing but scaling factor. And it can be extracted by passing above signal through a low pass filter. So already what I explained. Therefore, the output of the low pass filter is AC square by 2 cos phi m of t. Cos phi m of t we are getting. So if phi is equal to 0, cos 0 is nothing but 1. So what is the value we are getting? The maximum signal we are getting. If phi is equal to 90 degree plus or minus 90 degree. So what is the output we are getting? 0 output we are getting. Cos 90 is 0. So when phi is equal to 0, we are getting the maximum output, that is maximum signal, that is nothing but AC square by 2 m of t. AC square by 2 m of t. If phi is equal to 90 degrees, so cos phi, that is nothing but cos 90 degrees is equal to 0. Cos 90 is equal to 0. So what is the value we are getting here? V0 of t is equal to 0. Here V0 of t is equal to AC square by 2 m of t. So whenever phi is equal to plus or minus 90 degree, the output becomes 0. This effect we are calling it as a quadrature null effect. This quadrature null effect is occurring in DSBSC demodulation technique. In the coherent detector, only one drawback is there, that is nothing but quadrature null effect. So whenever we are maintaining the 90 degree phase shift, then the quadrature null effect is coming into the picture. Okay. So the demodulator, what it is doing? It is extracting the original information signal from the received signal. So what is the original information signal? M of t, what we have transmitted from the transmitter section. So finally the output of the DSBSC is nothing but AC square by 2 m of t. So this is about the DSBSC demodulation system. Next, I am concentrating on SSBSC modulation. So first we started with AM, then DSBSC, and now we are switching over to the SSBSC. So what do you mean by SSBSC? Single sideband suppressed carrier system. Single sideband suppressed carrier system or suppressed carrier modulation. So what is the meaning of that? In the previous chapter, we have discussed that DSBSC modulation and demodulation. The DSBSC modulation, there the modulated signal is containing the two sidebands. One is upper sideband, another one is the lower sideband. So the two sidebands having the same information. So upper sideband is having the same information, lower sideband is also having the same information. So if two sidebands are having the same information, what is the need of transmitting the two sidebands at a time? So here what we are doing, we are suppressing one sideband and we are transmitting only single sideband. The single sideband should be either upper sideband or lower sideband. Why means both the sidebands are having the same information. So suppressing one sideband and concentrating only one sideband, we are calling it as a single sideband modulation system. That is single sideband suppressed carrier modulation system. So what is the diagrammatical representation of the SSBSC? So SSBSC here lower sideband we are removing, carrier also we are removing, only upper sideband only we are transmitting. Okay, only one sideband, that is upper sideband only we are transmitting. Another way, we can remove upper sideband, we can remove the carrier signal, only we can transmit the lower sideband. Either we can transmit the lower sideband or we can transmit the upper sideband by using the SSBSC modulation technique. Okay, so here the power whatever is required for the transmission of the two sidebands and the power whatever we are required for the transmission of the single sideband. So we are saving the lot of amount of the power by transmitting only single sideband. And the power whatever we are saving by subtracting the carrier and one sideband, that saved power we are utilizing for the transmission of the single sideband. So in the single sideband system, we are effectively transmitting the signal with higher concentration, and at the receiver we can easily detect to the original information even though noise is there. Okay, so now, so in the above figure, the carrier and sidebands are suppressed, only the upper sideband we are using. So another way is we can use the lower sideband also. So then what is the mathematical expression? SSB modulation. So we have to get the modulated wave. So for that modulated wave, we have to represent that modulated wave by using mathematically. So the mathematical expression for the SSBS is, let us consider the same mathematical expression for the modulating and carrier signal as we have considered in the earlier chapter. So what we have taken? Modulating signal we have taken AM cos 2 pi FMT. What is the carrier signal we have taken? AC cos 2 pi FCT. So the mathematically how we are representing the SSBSC? SSBSC we are representing mathematically such a way that S of t is equal to AM AC square cos 2 pi FC plus FM into T, or AM AC square cos 2 pi FC minus FM into T for the lower sideband. This is for the USB upper sideband. This is for the LSB lower sideband. This term is square, AC square. This is AC square. AM AC square. Why means AC cos 2 pi FCT is there. At the receiver also we are multiplying with the AC cos 2 pi FCT plus 5. So that why AC square we are getting. So AM AC square cos 2 pi FCT 2 pi FC plus FM into T, or AM AC square cos 2 pi FC minus FM into T. So upper sideband is there, lower sideband is there. Okay, any one we can transmit. So the next here we can take either this one, thus it nothing but S of t can be taken as AM AC square cos 2 pi FC plus FM into T for the transmission. Okay, or you can take this one for the transmission. Okay, so any one we can take, both are containing the same information. So next, what is the bandwidth required for the transmission of the SSBSC? So in the AM, what is the bandwidth? 2 FM. In the DSBSC, what is the bandwidth? 2 FM. So what is the bandwidth is required for the SSBSC? So in the previous DSBSC, 2 sidebands we are transmitting. So 2 sidebands we are transmitting means the bandwidth of the DSBSC is 2 FM. But in SSBSC, only single sideband we are transmitting. So instead of transmitting the 2 sidebands, only single sideband we are concentrating and we are transmitting the single sideband. So the FM DSBSC bandwidth is 2 FM. DSBSC bandwidth is 2 FM. 2 FM for 2 sideband transmission. 2 sidebands transmission. Single sideband transmission 2 FM divided by 2 for single sideband transmission. Single sideband transmission. So how much bandwidth is required? The bandwidth required for the SSBSC is FM. Bandwidth required for the SSBSC is FM. Okay, only FM bandwidth is required for the SSBSC. So next, so what is the power? So the lowest bandwidth is required and most of the applications we are preparing SSBSC. Next, before discussing the power, so how much amount of the power we are saving by using the SSBSC is the question now. Okay, so we are switching over to the AM to the DSBSC. From AM to DSBSC, how much power we are saving? 66.6% of the power we are saving by suppressing the carrier. And next we are moving to the SSBSC. In SSBSC, how much amount of the power we are saving? The power saving, let us take power saving is given by PAM minus P SSB by PAM. So here PAM is nothing but PC plus PC mu square by 2 minus PSSB. PSSBSC is nothing but PC mu square by 4 divided by PC plus PC mu square by 2. So in the top PC is the common, bottom PC is the common. So PC I am cancelling. So what is the value we are getting here? 1 plus mu square by 2 minus mu square by 4 divided by 2 plus mu square by 2. So if I am simplifying this one, 4 plus 2 mu square minus mu square by 4 divided by 2 plus mu square by 2. 2 net cancel. What is the value we are getting here? 4 plus 2 mu square minus mu square becomes mu square divided by 4 plus 2 mu square. 4 plus 2 mu square. So let mu is nothing but modulation index is equal to 1. Mu is equal to 1. Mu is equal to 1 if you are substituting. So what is the value you are getting? 5 by 6. 5 by 6. What is the value of 5 by 6? 83.3. So by using the SSBSC, 83.3% of the power we are saving. Okay, 83.3% of the power we are saving. So this saved power we are effectively utilizing for the transmission of the single sideband. Okay, so now, so what is the power expression for the SSBSC? So this is the main advantage of the SSBSC. Okay, this much amount of the power we are saving. This much amount of the power we are saving by using the SSBSC. Okay, power we are saving by using SSBSC. So now mathematical expression for SSBSC. So what is the S of t? S of t is AM AC square cos 2 pi fc plus fm into t, okay, for the upper sideband, or fc minus fm into t for the lower sideband. Okay, one expression we are taking, either upper sideband or lower sideband, for the calculation of the power. Okay, so total power is P USB is equal to P LSB. Total power what we are utilizing for the transmission of either upper sideband or lower sideband. Okay, PT is equal to P USB is equal to P LSB. Okay, we know the standard formula for the power calculation. P is equal to V square by R. So here power, RMS power we are calculating. V RMS square by R. So VRMS already we know. VRMS is equal to Vm by root 2. VRMS is equal to Vm by root 2. What is the Vm? Vm is nothing but, this is the term. Vm is nothing but AM AC square is the Vm, maximum amplitude of the signal. Okay, so Vm by root 2 whole square by R. So what is the Vm? Here Vm is nothing but AC AM. AC AM by 2 root 2 whole square. So what is the value you are getting here? AM square AC square by 8R. AM square AC square by 8R. The value what we are getting here, this is the power. So P LSB is AM square AC square by 8R, or P USB is also AM square AC square by 8R. So the power expression for the SSBSC is AM square AC square by 8R. That is nothing but PC AM square by 4R. PC AM square by 4R. So this is the power requirement for the SSBSC. Mathematical expression is PC AM square by 4R, or AM square AC square by 8R. So now see here, what are the advantages are there by using the SSBSC? So first advantage of the SSBSC is bandwidth or spectrum space occupied is lesser than the AM and DSBSC wave. So the bandwidth required for the DSBSC is 2 FM. Bandwidth for the AM is 2 FM. Bandwidth for the SSBSC is FM. Okay, bandwidth required for the transmission of the information is FM by using the SSBSC, 2 FM by using the DSBSC, 2 FM by using the AM. Okay, is there any information degradation? No, same information we are transmitting by using the 2 FM bandwidth, by using the FM bandwidth. Okay, then transmission of more number of signals is allowed. What is the meaning of that? The bandwidth required for the transmission of one signal is very less, means large number of the signals we can transmit. So 2 kilohertz, 2 kilohertz, like that. If you are taking one signal is having the 2 kilohertz, so like that n number of signals we can transmit. Okay, if 10 kilohertz bandwidth is there, so 2 kilohertz is the signal bandwidth. Total channel bandwidth is 10 kilohertz. How many signals? 5 signals we can transmit. But DSBSC, if you are using, how many signals? Only 2.5 signals only we can transmit. Okay, 2.5 means 2 signals only we can transmit. So here is the number of signals is going on increasing by using the SSBSC modulation technique. And next power is saved. So already we discussed. In the AM, large amount of the power is concentrated in the carrier. Okay, by using DSBSC we are saving 66.6% of the power. By using SSBSC we are saving 83.3% of the power. Okay, large amount of the power can be saved by using the SSBSC. Okay, that is the advantage. High power can be transmitted. High power signal can be transmitted. What is the meaning of that? So the saved power, whatever it is there, 83.3% of the power we are saving. No, that saved power we are utilizing for effective transmission of the single sideband. Whatever the single sideband we are transmitting, no, that single sideband we are using the saved power for transmission of the single sideband. Okay, is power whatever it is there, that we are utilizing for the transmission of the single sideband. So high power means effectively we can transmit the signal for the longer distance without any degradation. If there any deviation is there in the signal also, we can extract at the receiver side. Okay, less amount of the noise is present. As the signal strength is good, even though noise is there, that cannot be affect the original information signal. Okay, next, what are the disadvantages? The disadvantage of the SSBS is generation and detection of the SSB wave is complex process. So only the detection and generation of the SSBS is somewhat complicated. Okay, next, quality of the signal gets affected unless the SSB transmitter and receiver have an excellent frequency stability. So here the coherent detector we are using, the frequency stability also we have to maintain. Whatever the signal we are generating at the transmitter side, whatever the signal we are generating at the local oscillator, so those should be the stable signal, should be in phase and should be in the same frequency. Okay, next, what are the applications of the SSBSC? Power saving requirements and low bandwidth requirements is main advantage. This advantage we are effectively utilizing for the so many applications. What are those applications? Inland, air and maritime mobile communications. So in mobile communication systems we are using, point to point communication we are using, in radio communication also we are using, in television, telemetry, radar systems and in satellite communication systems we are using SSBSC modulation system. Okay, so this is about the different types of modulators. Among those different types of modulator, SSBSC modulation is the better one. Okay, so what we are discussing today lecture, we are concentrated what are the demodulation technique we are using for the detection of the DSBSC. So coherent detector we are concentrated. Next, what is the SSBSC? Okay, and what is the bandwidth required for the SSBSC, and what is the mathematical expression for the SSBSC, and what is the power consumption for the SSBSC. So what is the power saving of the SSBSC, and what are the advantages of the SSBSC, what are the drawbacks of the SSBSC, and what are the applications of the SSBSC we have discussed in today's lecture. Okay, thank you.